The next topic we're going to cover before looking at a couple examples is our initial and final value theorems. And so these are going to be useful for checking the validity of our f of s before we inverse transform to f of t. So to make more sense of that, I've copied this figure that we had from our very first video in this unit. And so keep in mind, we're starting with a problem in our time domain. We are then Laplace transforming to frequency, where we do our analysis, and then we inverse Laplace transform back to our time domain and get our final solution. So as we're going to see in later videos, this process of inverse Laplace transforming isn't always easy, and it can sometimes be quite time consuming. So it's useful to make sure that we've done our analysis correctly before going through that process. And so our initial and final value theorems allow us sort of a quick check there. So let's go ahead and state what these two theorems are. So starting with our initial value theorem. So our initial value theorem says that the limit as t goes to 0 plus of f of t is equal to the limit as s goes to infinity of f of s times f of s. And so we'll see how we can apply these theorems, but if we think about it, we can say essentially, if we know our f of t, we say what's the value right after 0, and then we can check, we'll have some function in terms of s's, we multiply that by s, and then we let s go to infinity, and the result should be the same as the numerical value for our limit in the time domain. One thing to note is that this initial value theorem will not work if we have impulses. So it does not work with impulses. And so by impulses, I mean our deltas. So our delta of t in our f of t. And so that makes sense because we notice we're defining this limit as t goes to 0 plus in time. And so remember, our deltas are kind of a weird mathematical thing where they're right at 0. Okay, so our final value theorem So in this case, we're going to be looking at the final value of our time domain function. So the limit as t goes to infinity of f of t is equal to the limit as s goes to 0 of s times f of s. So we can see sort of this duality between our time and frequency domains. And so of course, this is only going to be useful if we have some finite value for our f of infinity. Only useful if our f of infinity exists. For example, maybe it's a function that just keeps on increasing infinitely, so we don't necessarily have a finite value. So this isn't necessarily always going to be applicable either. We then have a restriction for both of these theorems, and it relates to something called the poles of our system. And so I'll come back and describe this in a little more detail in a second. So both of these theorems only hold if our poles are in the left half complex plane. So only hold if the poles are in the left half plane. And so oftentimes this is a big topic that comes up in control systems, for instance. We'll just abbreviate that as LHP. Left half plane, and so what the plane we're talking about here is the complex plane. So complex plane, or we'll also refer to it as our S-plane. And so there is one exception here. We can have a simple pole at the origin. So except for a simple pole at the origin. So let's sort of describe a couple of things in this statement in a little more detail. So in general, our f of s function is going to be some function of s, and we can write a general form where we have some constant k, and several equations up in the numerator. So I'm going to write it as s plus z1 times s plus z2 dot 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 times s plus z sub n. In the denominator, I can say sort of a similar generalization, s plus p1 times s plus p2 dot 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 all the way out to some s plus p sub m. And so what we call these things in the general term, as I said earlier, our k is just our constant, but the zeros come from the numerator terms. So we would say that zeros of f of s are at negative z1, negative z2, so on and so forth, all the way to negative z sub n. And so basically these zeros are any value of s that are going to make our f of s equal to 0. So for example, if we plug in negative z1 here, this whole term in parentheses will go to 0, and therefore our f of s will be equal to 0. Now in the denominator, we can figure out what our poles of f of s are. So from the denominator, we have our poles are negative p1, negative p2, so on and so forth up to negative pm. And so note that m and p don't necessarily have to be equal, so we can have different numbers of poles and zeros. But in this case, our poles are defined as values where our denominator becomes 0, which makes our transfer function, or rather our f of s, sorry, not our transfer function, makes our f of s infinite. So if we plug in, for instance, negative p1 here, this whole term in parentheses goes to 0, and then we have something divided by 0. So coming back to this idea of our complex plane, or our S-plane, so we can think about what this looks like graphically. So here if we have our S-plane, and so remember in general we said for this unit we're saying S is equal to sigma plus j omega. So here we have our real axis, or our sigma, and over here for our vertical axis we have j omega. So we have real on the horizontal, imaginary on the vertical. And what we're saying sort of our safe space is over here in this area. And so let me actually just highlight instead maybe. So basically anywhere over here, this is all our left half plane. So anywhere to the left of that imaginary axis. So this is our left half plane. So we want all of our poles to be in this left half plane for initial and final value theorems to hold. And so we can see this from our f of s function here, or in some cases you might have a plot of poles and zeros. And so what those can be plotted as is typically our zeros are going to be an open circle and our poles are going to be x's. And so these don't necessarily have to be real valued. So keep in mind these poles and zeros, so these z1s, z2s, z3s, so on and so forth, and our p's can also be complex valued. So maybe we have a pole up here. So we have something that looks like that. So we have two poles in our system that have some real part and some imaginary part. But because they're still in this left half plane, our initial and final value theorems still hold.